Uh, Hello, good morning. Happy Holi to all. Hope you are all well. Okay, and let me introduce myself first. I am Shomajit Punia, PhD research student, Spring 2021, on behalf of the Department of Economic Science, IIT Kanpur. And this is actually my turn paper presentation, and thank you for being a part of the presentation here. And this paper basically goes to ECO 758A, that is topics in growth economics. Okay, now I will start my paper presentation. Okay, hopefully I share my screen. Just wait for Hopefully I am able to share my screen. Okay, the 755A. Oh, fine. Okay, topics in growth economics. And the title of my paper is the effects of robots on the long run economic growth. And the authors are Jun Liu, Long Ren, Jiang Chu, and Dating Gong. All the authors are Chinese economists, and these names are actually some sorts of difficult to pronunciate. Okay, that's no problem. Okay, let's move on our main introduction part. Okay. Rapid development of artificial technology, right? It's all about the technological advancement. And the robotics revolution is rapidly accelerating day by day as fast-paced the technological advances in automation, engineering, energy storage, artificial intelligence, and the machine learning ability or coverage. And already the number of robots in use, the worldwide multiplied threefold over the past 2 decades to 2.25 million. And the trend suggests that the global stock of robots will multiply even faster in the next 20 years, reaching as many as 20 million by 2030 by the 14 million in China alone. And you all know that the Chinese economy are too much advances in their robot technology, and this is one kind of the first robotics country, and we all know that. And the rise of robots will obviously boost economic productivity and economic growth. And we also observe, as our main objective of this paper is to see the effects of the robots on the long run economic growth. That is the basically on the impact of growth, right? Okay. And countries around the world are utilizing more and more robots. And with the rapid development of the artificial intelligence technology, the application of robot is widening and deepening. And due to the fact that the robots are the capable of machine learning and deep learning, as we also mentioned earlier, and we will also see later, and we made a powerful assumption regarding the machine learning ability of robot. And in our last phase, we also show you that how there is a vast difference when a robot has the capable of machine learning ability and when the robot has takes no machine learning ability. We will come later on. And here we start our model with the theoretical production process by considering the difference in the learning by doing ability. And the concept of learning by doing ability has been used by Arrow, and we all are familiar with that from our undergraduate studies, that the concept of learning by doing has been used by the Arrow, Kenneth Arrow, basically, in his design of the endogenous growth theory to explain the effects of the innovation and the technological change. And, based on the influence of robots on the long term growth is also invested, and we also show later on, as you understand from the paper, that the effects of robots in the long run economic growth. And the countries around the world are utilizing more and more robots, especially in case of the Chinese or the US economy. You will observe that you will get a clear cut picture, right? Now I come to some examples. For instance, on October 27, 2017, According to a report by CNBC, the retail giant Walmart has deployed self-scanning robots in 50 locations in the United States, which are mainly used to check the inventory, prices, and the misplaced items. And from here, you understand that how the technology has advances and nowadays. And if you look in YouTube or search in some social media, you will see that in the US economy or in the Chinese economy, robots can also be used or played a role as a chef in the restaurant, right? So nowadays, seriously, robot has mastered all the human activity. Okay, and robot also can surpass the general intelligence of human beings. Now we came to our next slide, and here we are trying to address the following research questions. Basically, we are not trying, but the authors of this paper are trying to address the following research questions: that what are the impact of robots on the long run on the output and the return gap under the perfect competition conditions. We will show mathematically that this concept in our later slide. Our second question is that what are the impact of robots on the long run economic growth rate? And this is the main important point that we have seen. And will the use of robots lead to the economic to a sustained growth path? And finally, what factors influence the long-term economic growth rate? Is there any optimal robot investment ratio? Yes, this is a kind of, I think, limitation to maximize the long-run growth rate of output. We also see later that this is one kind of limitation. And in the first slide, I also wrote down in bullet 4 that advantages and disadvantages of robot investment. Obviously, there are some advantages. Existing empirical studies support the point that the use of industrial robots can increase the labor productivity that we have mentioned earlier. But if you look at that, some literature suggests that the right substitution effect of robots will inhibit the growth of the employment and wages, thus prohibiting the increase of the investment. So it's, you think that it's a kind of a barrier, actually it is. And as a result, it leads to a reduction of the welfare of the youngsters. Youngsters in the sense that actually young workers actually. That is the young labor force, that is 50 to 59 or whatever maybe. That's a kind of disadvantage, you know, and that robots are taking your jobs actually, and there may be a negative impact or effect on some labor segment, and it can obviously surpass the general intelligence or human beings. Actually, one kind of disadvantage. Okay, next. We now come to our theoretical model. Here we come to elaborate the model actually, and that there are basically two main characteristics of robots in the production process. First, replacement role of the robots in the labor force, and we will show later that how robot replace in place of labor force, and it will master, and how the productivity of robot vastly greater than the human labor force actually. And the second characteristic is the machine learning ability of robots, and we will see later that what is the difference when a robot can obtain a machine learning ability and when not. And we establish a theoretical model considering these two characteristics of robot, right? And here we introduce a Pretner model, which is a kind of you say that it's a kind of extension of Solow model, uh, though it was not an extension, but a kind of extension of Solow growth model, and it is a kind of a benchmark model, right? Pretner model. Now we go to next slide. Oh, okay. Now here we consider the Cobb-Douglas production function. We are all familiar with the Cobb-Douglas production function from our undergraduate studies, that yt equals to at lt k to the power alpha kt to the power beta, that is alpha plus beta equals to 1, so beta equals to 1 minus alpha. But here the Cobb-Douglas production function is slightly modified. Here is we can incorporate the term a new term RT, that is the robot technology, or whatever you can say, amount of robots actually, and the whole function we can written as yt equals to at rt plus lt whole to the power alpha and kt to the power beta, where yt equals to have the usual meaning. That means yt equals to amount of output at time period t. Your at is technological progress, or at time t. Lt is the labor force, that is the amount of labor. Rt is the amount of robot at time period t. And your kt, oh, I am missing the term kt here, is kt is the amount of capital at time period t. And alpha and beta, as we all know, that alpha is the that is a share of output in the robot and labor, and beta is the share of capital. And Cobb-Douglas follows the usual production function properties, and you are all familiar with the production function properties. That means the important that first is the CRS technology, that means alpha beta equals to 1, that means it follows the constant return to scale. And the Cobb-Douglas production function also follows the diminishing marginal returns, and it also satisfies the usual in other conditions. And in this production function, labor and capital are incomplete substitutes, while labor and robots are complete substitutes. And finally, you all know this, that it is assumed to be, that is the technological progress is assumed to be completely exogenous, right? Now, the above model is extended to a new model as yt equals to, that means if you see in the previous slide, that means yt equals to at, that means in the next slide we can incorporate the term art and alt into our slightly into our the first bracket. So our equation becomes yt equals to art into rt plus alt into lt whole to the power alpha k to the power 1 minus alpha, where alpha plus beta equals to 1. And we assume a powerful assumption that the robot has the ability of machine learning, and with the accumulation of knowledge and capital, the work efficiency of robots will increase significantly, and you also we all know that. And now, based on the idea of learning by doing, basically the ideas given by Arrow of endogenous growth theory, our ART can be expressed as just following: ART equals to bk t to the power theta, and where beta b positive is strictly positive and theta also strictly positive. And your ART is nothing but the working efficiency of robots. And in that case, ALT can also be expressed as ALT equals to ck to the power lambda, where C is strictly positive and lambda also strictly positive, where your the term ALT is nothing but the working efficiency of labor. And we also assume that the speed of the machine learning of the robot are much faster than the labor force. It's obviously true, and we also show mathematically, that means your theta, that means your theta is nothing but the learning ability of robot, and your lambda is the learning ability of your capital, learning ability of your labor. So it's the speed of the machine learning robots are much faster than the labor force. So is your theta is strictly greater than your lambda, right? Okay. Now, if I plug the values of ART and LT, that means ART equals to bkt to the power theta and LT equals to ck to the power lambda into our main equation, that means the original equation, that means y equals to ART into RT plus LT into LT. So what we get is that yt equals to bk to the theta. Just plug the values of ART into the main equation, we end up getting the following expression. And this is our main equation, right? Okay. We now skip into our next phase. That is, we are now able to explain the comparative static analysis and the long run equilibrium. And in perfect competition, we can obtain the return of robot, that is W, we denote by WRT, the wage of the labor force WLT, and the return to traditional capital WKT. And this assumption that is that the authors have made in their first research questions, that is the perfect competition, so return rate actually. And what we get is that WRT equals to delta YT by delta RT, and that means how we get. So it's simply nothing but you can differentiate partially with respect to RT. So your previous equation, that means this equation, YT equals to BKT to theta. So here you can actually partially differentiate this YT with respect to this RT. We end up getting the following expression as follows. And now the wage of the labor force WLT equals to dyT by delta LT, not D but delta, as it's the partial derivative. So what we are getting? So we are end up with this following expression. And similarly, we can also get the return to traditional our capital, that is WKT. Such the equation looks like. The equations are look like very weird, but this is not weird if you it's too much easy. So if you can calculate this, so you can easily find out this equation. So how can you calculate? So simply differentiate partially with respect to your the following terms. So here what you are doing, that KT, that means your differentiate YT with respect to the KT. So what you are getting, you end up getting by the following this expression. Hope this is clear too. Now from this, we also draw a following proposition. Basically, we are not drawing, but the authors are drawing the following proposition that with other parameters unchanged, the output is increasingly concave in the input of robots. Now, what does it mean actually? Now, this proposition implies that if we add more and more input initially, it will increase the input productivity of output, but after a certain level, it will diminish. That means it exhibits a diminishing marginal returns to scale. And if we like to show this proposition, that means mathematically, that means what concave function means actually, that means your first order derivative is strictly positive and your second order derivative is strictly negative. So you can also get from this equation also, that means the delta YT by delta T, it is obviously strictly positive, and you can take the second order derivative again, that is d2YT by dRT2. So what we get is obviously strictly negative, right? And your alpha lies between 0 and 1. Now we come to next slide. That means our proposition 2. What it says that the return gap between the robots and the labor depends on the learning ability of robots and labor. That is when, what does it mean actually? That when the learning ability of robots is stronger than the labor force, right? Then the return gap between the robot and the labor increases as the capital input increases, and we can see the reverse. Yeah, that means when the learning ability of robot is not stronger than the labor force, that means your labor force is stronger than the learning ability of robots. So we can see the reverse result. That is when robots are better learning than the workforce, right? That means your theta minus lambda is strictly positive, as we also show earlier. That means your theta is very, very strictly greater than lambda. We have the shown earlier. That is your WR by WL is also B by C KT theta to the power theta minus lambda, which is strictly positive. It is our presumption that one day In future, robot will master all kind of the human activities, including skill and knowledge. And if you have any doubt, I also provided the URL of the paper, and you can see the derivations in the appendix of the last portion of the paper. Okay. Okay. Next. Now we come to the long run equilibrium analysis. We can derive the long run equilibrium now. That means your rate of change of capital stock. So here we are basically want to derive the steady state equilibrium. So what we get is K naught T equals to S of KT. S of basically it's S of uh, YT. That means for if S into f of kt, this is nothing but the production function. That means f of kt, that means yt into kt minus delta kt. So if we plug the values, we end up getting by the following expression. Similarly, the rate of change of robot, we also get like this, right? Now, next, we now determine the growth rates, and the determination of growth rates are very, very important. Uh, we now determine the growth rates of our traditional capital and the robots. If we symbolically, we can also may write GK and GR respectively. So what we get if we derive the growth rates, we just get S into 1 minus SR, your YT by your KT whole for alpha minus delta. Now, how we get this expression? Hopefully, I am not able to show you the derivation as there is no instrument. Uh, so, hopefully, if you are able to see these derivations, I can attach my handwriting script actually. So how we get actually, so you can also easily see that just simply take the log values of kt and simply differentiate. So what we get, we end up getting by this following expression. So what we get if you take the log version of kt, uh, so if I differentiate of log of kt, so what we get that 1 by kt into dkt by dk by dt. So dk, we may write that dk by dt equals to k naught. So k naught by kt equals to your s into 1 minus sr bkt and something by kt minus L. We have end up getting by this following expression. And similarly, we can also determine the growth rate of robot. So the expression is look like. The expression is looks pretty weird, but if you solve in your by your own hand, so it's very much easy. You know, in per capita terms, the growth rates can also be written as like this. We end up getting by this following expression. Now, from this, we can draw another proposition that when the learning ability of robot is stronger than the human capital, there will be no balanced growth path for the economy, and the economy will eventually show a sustained growth pattern, and the growth rate of capital per capita, output per capita, and robot per capita will keep growing. Now, we made a numerical analysis, but I am unable to write down the numerical table. So I will share the original paper so you can easily find out. Wait for a moment. Just wait. Hopefully, I am able to share my screen. This is the main paper. the numerical study. Here we consider a numerical analysis. Here we are basically comparing two respective scenarios, actually two respective situations. So number one, that when the robot has the machine learning ability and when the robot has no machine learning ability, right? And if we look the diagrams, number one, number two, and number three, see that there is a sharp difference between these two. Here we consider three scenarios differently, and at each scenario you will see the same picture. That means when the robot has the machine learning ability, the dotted lines here actually mentioned the dotted lines are always above the solid line. The dotted lines are the when the robot has the machine learning ability, and your solid line denote that when the growth rates of robot when the robot has the no machine learning ability. And you will see that in all the above cases, the dotted lines are always above the solid line. That is, the growth rates are higher when they have the machine learning ability compared to no machine learning ability. And here we consider three different diagrams or scenarios: growth rate of capital per capita, robot per capita, and output per capita. And by comparing these figures, we can conclude that uh, when the robots have the no machine learning ability, the growth rate of output per person will tend to be constant, and the growth rate of output will continue to increase when the robots have the machine learning capability that are stronger than the human labor force, right? That means you can one day the robot will master all kind of human activity, right? And okay, now I will again back to my original slide. Okay, I am able to hope I am able to share my screen. Okay. Okay. Next, we illustrate the relationship between the robot learning ability and the per capita growth rate of our growth rate output. That means per capita output growth rate. And this is on the basis of the numerical analysis. Basically, these are obviously on the empirical studies and numerical analysis. And here we see, if we plot the values, we see that there is a positive relationship between these two. That means if your robot learning ability increases, obviously your obviously growth rate increases. So the line is increasing, so is an increasing function of the growth rate. So next, from this we can draw a following proposition that the robot learning ability and per capita output growth rate are positively related. We also show graphically. Graphically, it's clear too easy to understand that there is a positive relationship. So the line is the upward rising, right? Okay. Next, with the rapid progress of the artificial technology, the learning ability of robot will increase in the long run. Next, we also show that there is a relationship between the percentage of total saving invested in robots and per capita output growth rate, right? We show graphically. That means from this we can draw another proposition. Here graphically what we see that initially it increases, but after a certain level it diminishes. So here we can see the relationship between the percentage of total saving investment in robots and the per capita output growth rate. And from this we can draw a following proposition that there is an optimal robot investment ratio to maximize the long run growth rate of output per capita. And this point is a very important as we also mentioned earlier in my introduction portion, that this is one of the limitation actually, that optimal robot investment. That means too much robot investment is not a good. Too much robot investment basically it shows a negative impact on the growth rate of the economy. And we also show graphically that initially it increases, but after a certain level it diminishes. So the shape of this just like an inverted U shape, and once it has a negative growth rate also, it may be achieved a negative growth rate also, but the negative growth rate is actually our outside the concept of the economics, right? Okay. Now we reach to our conclusion that the AI technology and the rapid development of the robot technology have brought new power in various fields. Okay. And we also consider robot as a unique factor of production, not only considering its substitution effect on labor force, but also considering its essential difference from labor force. And we believe that the difference mainly comes from the application of the AI technology of the robot, so that it has the machine learning ability, and this ability may surpass the human labor force in the near future. And one day it may be happen that robot will master the all kind of human technology, all kind of human activities, and it will clearly remove the human labor force. But wait for a moment. And the idea basically comes from the learning by doing, and this paper analyzes the impact of use of robots on the long run economic growth. Our result also show that we also mentioned in the propositions that with the parameters unchanged, the output is increasingly concave. The return cap of robots and the labor force depends on the learning ability of robots and labor. And when the learning ability of robots is stronger than human capital, there is actually no balanced growth path for the economy, and the economy will eventually show a sustained growth pattern, right? And the growth rate of output per capita will keep it growing. That means your growth rate of capital per capita, output per capita will constant. That means increasing. And no, sorry, not constant, but growing over the time, that over the long run period. And our fourth proposition is that the robot learning ability and the per capita output growth rate are positively related. We also show graphically. And finally, the optimal robot investment, we also show this graphically also, the inverted U-shaped curve. That means your optimal robot investment. And in our paper, we conclude that the application of robot may boost the economy to some extent. However, more robots are not always better. We also see in the proposition 5 that there is an optimal robot investment ratio to maximize the long run output growth rate of per capita. We also show earlier. And the as for developed countries, the application of robots provides favorable conditions for them to carry out the reindustrialization. I also mentioned in here the second bullet point, to reshape the national manufacturing competitiveness and developing the emerging industries. And we may conclude that, however, more robots are not always better. And combined with proposition 5, managers should not only increase the investment in robots. How to improve the learning ability of robots is also of great importance. That means your optimal robot investment is very, very necessary for all the managers of the managerial sections of each and every company. So how to improve the learning ability of robot is the main importance, is also of great importance, right? Thus we conclude our lecture. Thank you.